Okay, we're doing example 1 on section 3.1. This is really just an example to show kind of how limits work, what the definition means, as you see on the worksheet there, the limit of a function definition. So example 1 says find the limit as x approaches 1 for f of x, where f of x is equal to x squared minus 1 over x minus 1. So what we're going to want to do here is we can make it, if you read the definition of what it is to be for this limit to exist, it says that as we get closer and closer to this value 1, we want the y values to approach some particular number. So the best way to sort of show what's happening here is to make a table of values. So what we're going to do, again, this is just sort of the first way that we're going to evaluate limits. We have better ways to do this than making a table, but just to sort of show exactly what's happening here. So the idea is that we want to pick values of x that are very close to 1, but not equal to 1. Okay, so what we're going to do, we're going to start out by picking negative, sorry, not negative, we want to make that positive 0.5, close to 1 is what we're looking for there. So we're going to make that 0.5, that's kind of close to 1. We're going to try 0.9, that's even closer. We're going to try 0.99, and that should probably be enough. And then on the table, we're going to just go ahead and put the number 1 here. But as you see, if you try to actually plug the number 1 into the function, you have this problem of dividing by 0, so there's no output value there. So I'll just put an x. We're also going to go on the other side of 1, so we'll put 1.01. That's kind of close. On the other side, we're going to put 1.1, and we're going to put 1.5. Okay, to help us figure out what these values are going to be, we can notice that this function is actually the same as this, x minus 1. You can also just use a calculator on this if you want to. X plus 1, if you factor that as the difference of squares. And you can notice that you can't really cancel these x minus 1s right now, but we'll notice later that this function will act almost exactly like x plus 1. So if I plug in 0.5, we're going to get, and you can verify this on the calculator, if I plug in 0.5, I'm going to get 1.5. If I plug in 0.9, I'm going to get 1.9. If I plug in 0.99, I'm going to get, as an output value, 1.99. And again, what we're doing here is we're taking all these x values that I put on this, and we're basically plugging them right into the function there. So like I say, if you want to verify this on your own, on your calculator, go ahead and do that. But this is the output values that you're going to get. If I plug in 1.01, I'm going to get 2.01, and I'm going to get 2.1 here, and I'm going to get 2.5 here. So what we need to notice here is that the closer that I get on either side to 1 on the x values, the closer that my y values seem to be getting to the number 2. 1.99 here, 2.01 here. Pretty close to 2. In fact, if I were to get even closer to the number 1, like put 0.999, 1.001, we'd find that the output values are yet closer to 2. So what we can conclude from this is that the limit as we approach 1, limit as x approaches 1 for this function f of x, I'm going to try to get a better marker here. This one's not working so well. The limit as x approaches 1 of f of x is equal to 2. So based on the table, that's what we can conclude here. So this is called a numerical method of finding limits as we approach a particular value. You want to pick the values that are pretty close to this number right here, the limit as x is approaching, plug all these values into the function and see what the output values do. In this case, we notice that they do approach a number, so that number we can call the limit.